Oh. Net with us?
Of course. No pressure. Part of it. Just if you feel
comfortable. Okay, great.
Okay, I guess we can start with the second talk of the day with Luis Campusano from Universidad de Chile. Then we'll talk about dark clusters of megaparsec scales. Please.
Okay, thank you.
Ho, ho, ho.
Okay, first of all, thank you very much to the organizing committee, and a pleasure to be here at the Universidad Estadual Sao Paulo and the ICTP, of course. So, well, I have the honor of being the senior person in this meeting, which is overwhelming for me. And in a sense, I can tell you this is an LSST motivated meeting, and have seen LSST emerging from zero, from looking for the site testing and Seropachan and everything. And I have been to some LSST meetings in Tucson, and I think that LSST is going to form the way astronomy is done. And you are the people who are going to be doing the work. I'm just going to look at the news, what was coming out. But the word transformational, I really believe it is, this instrumentation is something that for my period, it was unbelievable to have such a project. And I hope from Chile, from Chile we have so many projects going on, and you could be a bit surprised that a few people from Chile are here, but essentially we are overwhelmed by the number and the size of the project. So, my place is the Universidad de Chile, and I belong also to the Center CATA, which is for astronomy and applied technologies, which is mainly 3 universities in Chile. This is the team which are responsible for what I'm going to tell you. Is Gabriel Marinello he's currently at the Joint ALMA Observatory, and Roger Close, it's a long-time collaborator at the University of Central Lancashire in UK. Then Christopher Haynes, which is a former PhD student of mine, and he has become one of the experts in clusters. He was a very key element in the development of the cluster finder we produced. And then we have this Nancy Hitchfeld, which is a computing scientist. This is the result of the team between astronomers and computing scientists, which has an advantage in the sense that they don't have a priori, so they don't know what has to be found, and they worry about perfect doing the calculations. And it has been a great pleasure to collaborate with them in this data mining project. And then we have Daniel Pizarro and Sebastián Pereira. They both were master students from computing science, and they had a specific objective for their thesis. And the first version of the algorithm was done by Daniel Pizarro, and he is in industry now. He used to be at the University of Chile. And Sebastián Pereira, he did the latest version with us, and he is currently at INRIA, in Chile, which is this French Institute of Applied Research. And then Ilona Sochting, also a former student of mine, together with Roger Close, who used to be at University of Oxford, but now moved to the industry also, and she's in Finland currently. Okay, so so let me put the abstract. I want to take not so much time. So the abstract is what is the bottom line of what I want to say. And we did an exercise with a very well-studied sample of galaxies, DF, and we found that in the collection of clusters, we found that about a third of our detection known previously, and we had to deal with the explanation why an important number of clusters, I will define what is I understand by clusters, why they would have been missed. And this article was published, was online yesterday in Astrophysical Journal, and the study is basically in the nearby universe, that is of the order of 0.05 in redshift. The reason for these objects to be missed so far, we concluded that it is in the different galaxy contents. That means clusters of galaxies were discovered through light, and soon after we learned that the dominant component of cluster is dark matter, right? In essence, what we are dealing with is megaparsec size structures of dark matter with a given range of mass. And the question naturally is, what is the accompanying galaxy population? And we have learned that essentially it's dominated by elliptic galaxies in a very central fashion and agglomerated. And we released that condition so as to look for the massive structures, dark matter structure, and then we analyze what was the galaxy components. So essentially we find that these new clusters, in the sense that they are as massive of the well-known conventional clusters, they have fewer galaxies, less luminous galaxies, and less packed galaxies. So they appear very much as the field, and therefore for 2D searches it's difficult to detect them, and for their detection I believe we need very probably, I'm not sure whether photo C will do the work. And what is the theoretical context that could explain this is what is called the dark matter assembly bias. So there is a theoretical expectation that the actual appearance of cluster could be related to the history of the agglomeration of dark matter. So, in essence, this is it seems to, we are claiming we have found an important fraction of new massive clusters, and that puts new constraints for the theory of galaxy evolution. Okay, so what is the mind motivation? I mean, what is the philosophy behind this exercise? So the question is whether massive dark matter systems of megaparsec scale have single galaxy constituency. That is to say, whether the mass to light ratio of this structure can vary significantly or not. We have examples in the galaxy scales of for example, ultra faint galaxies, which are we have very few stars, these ultra faint galaxies, and very high mass over L ratios found by Simon and Giga, and also from in the cluster side, it has been done by researchers in Brazil, and Proctor et al. And I consider to be important that there was a recent paper by Nusinov and Sang that consider why the dark matter particles have not been detected so far, and there were some considerations that I thought they were relevant to the subjects of agglomeration of dark matter. And one last issue is that we have a theoretician group mainly working on inflation. We have some of our members from the University of Chile that work on inflation. And also we have a theorist, Anton Baushev, that works on plasma physics. And he studied the simulations of galaxies, and he studied the possibility that the universal dark matter profile, like Navarro, Frank, and White profile, could be related sometimes to some numerical artifacts. So in this paper, it is tested whether the simulation can have some numerical artifact behind these big black boxes that we are used to. And my association is that whether every dark matter cluster of megaparsec size actually has a single cluster dark matter profile. In essence, to my mind, it appears, it is not obvious that all the dark matter profiles of clusters is the same. So this is the general motivation of that. Normally, people cannot do this thing because the theoretical expectations are different, and you're very forced these days, not these days only, but in history, you're very forced by dominant views. So just a few words about dark matter assembly bias in case you have not heard of it. This was considered by Gao in 2005 and Croton 2007, and implies that the particular appearance of a cluster today depends on how the galaxy contained were established during the halo assembly. An evidence of this assembly bias, which is crucial, I understand from the conversation I have with my theoretical friends, it is a crucial element on the theory, and it was important to find it. And in 2016, it was announced, it was claimed that an effect of the assembly bias was found on a cluster set in the redshift range 0.1 to 0.3. So this was a work where there was a Japanese component and people from Princeton, and it was considered to be an important breakthrough on this issue. In simple words, it could say that equal mass clusters may have different galaxy associations depending on history. So it was not a single type of environment, a single type of galaxy contents, if this is actually true. Okay, so then now into the algorithm. Huh? So what was different? Why did we go into building a new optical finder? So, well, we decided that we did not want, as Ricardo mentioned on his talk, that it was a bit of a joke, he said, that when you compare the result of different cluster finder that they say they have a very small error, and you compare the catalogs, the overlapping is very reduced, right? So instead of getting a catalog of thousands of clusters, we wanted to check in the 2DF field, we wanted to check with all the previous catalogs that had been made, and we wanted to see if we, in particular, we were able to reproduce the Abell-type clusters. That is what Abell did, you know, with his associate, which was a wonderful work that even today is valid. We said we will try to reproduce the membership, we will try to reproduce the velocity dispersions and the centroids automatically. So if we do that, then we can say, okay, we reproduce everything which is known, and define which are new, and then investigate why or what are the characteristics of these new detections. So let me see. This is a Voronoi-based algorithm, which is very good because it contains all the information of the distribution of the galaxies. And then we added a gapper part, which is a separation between the galaxies from the background through a velocity gap. This was well tested and well adopted. It was introduced by Sabludov, Hukra, and Geller. And I will show you that it is one essential parameter of the algorithm, which is the velocity gap we consider for the objects within the clusters and the objects which are in the field. So the result of the application in the 2DF Galaxy Rapture Survey was the production of 1,900 clusters. For us, the definition of a cluster is everything that the cluster detects, starting from n equal 2. There is a bit of confusion in general because of the definition of clusters and the definition of groups. So this is a rather blurry limit, and there is not a clear physical separation between clusters and groups of galaxies. So we decided to use simply the denomination of cluster to all our detections. And then what we studied was the application of this cluster finding to a mock 2DF data coming from the Millennium simulation. So we work with the mock 2DF and validated the detections in the sense that for more than 10 galaxies, we showed that there was a completeness of 75% and a purity of 90%. I recall you that the completeness is the number of coincidence between the reference cluster catalog in this occasion is the simulation cluster catalog, and the purity is the fraction of our catalog, of our detection with respect to the reference catalog. So, and the other thing which was very important for us is that that the velocity dispersion we could determine were good tracers of the mass. So we checked that for more than 10 equal or more than 10 galaxies, the velocity dispersion determined by the cluster finder was a good indicator of mass. We are not, oh. It needs to be, sorry. Yeah, I need to push the button here every number of minutes. Okay, so the validation is done in a paper in 2017, last year, and we did a very detailed validation, and what I'm going to talk you today is the application of the cluster finding to the real 2D GRS sample. Well, this is an example of a conventional cluster, and I will argue that what we are finding is that we may have similar dark matter concentrations, but without those very bright galaxies. And so if we think that every bunch of dark matter comes this way, then we will argue that that is not always true. Okay, let me say what is new in the algorithm. In the algorithm, we do not take into consideration the biases that normally are, for example, in the Abell catalog. In the Abell an eyeball selection, they had to be a central concentration of galaxies, which is a bias of a particular association, and it had a luminosity dependent function, which is a bias also, and later on there were some progress in the sense that the machine APM, the APM EDCC catalogs were done in a digital. Before the digital surveys, you know, these things came from the digitation I belong to that old generation that had to fight with the plates. Okay, so how we are going to evaluate this fair evaluation if we are doing well? So we make use of the work, the excellent work done by the team from the 2DF. One of those workers is a friend of mine, is Roberto de Propris, currently in Finland, and he did a semi-automatic approach to reproduce, to rediscover the clusters that were found in the 2DF region by Abell and were found in the APM and in the EDC catalog. So he said, okay, I am going to make a redetermination of this well-known catalog in the old-fashioned way of finding clusters. And what he did was to use centroids from the catalogs, and he looked in central brightest galaxy and then searched for number of counts of galaxies within the same radius used by Abell. Abell used what is called the Abell radius. So the counting or the membership of the clusters were by the Propris was done through a radius of an Abell radius, which is in contrast to our cluster finding. We use an R200. We define the cluster through the virial radius. So, and we will see that makes some difference. So, the Propris selected by the Sablodoh-Hooke-Geller algorithm, and he computed mean redshifts, velocity dispersions, and centroids, and he got a new catalog. So it was a new determination, an semi-automatic determination, because the Propris started from the centroids given in the catalogs. Our approach does not start from centroids previously known, but is completely automatic. Okay, so this sample by the Propris was a benchmark for us. So we needed to know whether we could do it as well as the Propris, or if we were doing eventually better than the Propris. Okay. So. Okay, I just said already that we use R200 for the cluster core, where the galaxy counts and properties are evaluated. We made additional assumptions. We did not assume any profile, luminosity distribution. We did not use any of that, only position of the galaxies. And as I said, this was largely observationally driven, in the sense that we accepted that there was a dark matter domination, but we did not take as a fact that all clusters looked alike. Okay, so our idea was that in principle, the system of 10 to the 13, 10 to the 15 solar masses on a scale of megaparsec, they could in principle have a variety of galaxy contents. So this is the thesis. Is this true or is not true? Well, I am not going to extend on the properties of the 2DF Galaxy Redshift Survey, which is very old. People ask me, why did you use old survey? And I will give you the answer to that. So for young people like you, who maybe don't know about this, no, I know you know about the 2DF, because 2DF was too famous, so we cannot escape that, right? So we did something which Nelson is related here, is that we chose the same data set used by Eke et al., who search for galaxy groups. And the sample of galaxies that Eke used was 200,000 galaxies, and we chose exactly the same data set so as to compare their detection with our detections. And we adopted, for our cluster search, we adopted the lower limit of 0.009, and this is the redshift range of the sample. It's magnitude limited to 19.45. Okay, the algorithm is published in this 2017 paper. I am not going to go into any details. I refer you to the paper. The only thing I want to mention is it has two stages. It has a stage based on Voronoi, and it detects the concentrations and gives priority from high concentration to the lowest concentration. This is based on a maximum likelihood estimator developed by Allard and Fraley, which was introduced in 2 dimensions, and we generalized that to 3 dimensions. And the second stage, as I said, is searching R200. And the R200 is related to a separation between the cluster members and the field with this velocity gap that we chose to be 1,000 kilometers per second. 1,000 kilometers per second was the velocity gap used by the Propris, and it was shown by various workers that to be a good separation for this kind of sample. I said already that there was a compatibility between the sigma B for the Millennium cluster over the 300. There is a missing 0 there. In the 300 to 1,000 kilometers per second range, we had a very good relation with the simulation cluster coming from the simulations. Okay, this is a layout of the 2DF. In those days, this was really spectacular. So it has a northern part and it has a southern part, and it covers 1,800 square degrees. Essentially, the maximum likelihood operates in the sense that it has a concentration and start adding galaxies, and when the galaxies do not increase the probability that they are a separate population, then the growing of this structure is a stop. So from the geometric part, we took the potential galaxies, galaxy clusters, and in the second part, we took only the position of the centroids. And the second part is independent from the first part, which is related to the R200 and is related to the velocity gap. So, well, it has been mentioned in this meeting, the Voronoi and the way it works. And so we have a smallest cell, which is the higher concentration region, and it starts adding galaxies, and it gets into the limit where adding a galaxy, instead of increasing the probability, it decreases the probability. Normally, the representation of the cluster will be to the hull. The convex hull of the points will be the limit of the cluster. There is one issue which is important. In the construction of the clusters, we went from the higher priority, or you could say with the higher concentration, to the lower priority. And we did not allow members in common. That is, if a higher priority cluster was detected and then came another cluster being detected, if this another cluster had a galaxy that already was allocated to a previous cluster, this cluster was not allowed to grow. So in a sense, we gave a privilege to rather isolated clusters, and this was intentionally because we wanted interaction or interacting cluster, which would make more difficult the search for the virial radius and the search for a meaningful velocity dispersion. Okay, and we did not set a minimum number of galaxies, so the system detects from n equal 2 to n equal greatest number. This is from paper 1. It shows the relation from the Millennium velocity dispersion and the detection of our algorithm, which has a rather crazy name there. I just can say you that the BOs comes from Voronoi, and this plus G refers to the gap, velocity gap. So there is a Voronoi part and a velocity gap. Okay, the full cluster catalog has 1900 clusters and include 15,000 galaxies, that is 8.2 of the total. And the first thing we did is to compare with previous results, and we find that 90% of the cluster in this, what we call the full catalog, has counterparts in the two-peak catalog. That means we wanted to make sure that we're not finding a spurious thing. If somebody else looks carefully, then there should be a high degree of superposition between detection. So taking the whole thing, 90%, there was a not exact correlation, but there was a positional proximity. And we found that 73% of the DPO, the Propris sample, was contained in this full, what we call the full catalog. Okay, so the physics is what we care for, but before that, this is the distribution of all the groups or clusters that we found. This is the code for velocity dispersion. This is the code for the multiplicity. And you see that, well, the large scale structure is well recognized. And, well, from the point of view, the large scale structure, the cluster results make sense. It makes sense. This is the southern part of the thing. Okay, so as I said, we wanted to know the galaxy content within our clusters. And for that, we use a parameter that existed in the original survey, which is an spectroscopic parameter, and it separates the member galaxies of the sample into two bins. One, the early type galaxies, which are elliptical and S0, and late type galaxies, which are spirals and irregular. So we have a number associated with every galaxy in the 2DF that produced a classification between early type galaxies and late type galaxies. Okay, so I said already that we have exactly the same database as at the group search of 2peak, which I can say that it was quite different. The objective was quite different. And they found, for NG greater or equal than 2, they found 29,000 groups. So we find 1,900, they found 1,000. And that was 2.25. So it is a different way of doing things, okay? Our full cluster sample is 15 times smaller than the 2peak one and contains 170 of as many galaxies. I said that 90% of the cluster have correspondence between these two catalogs. Of our catalog, correspondence with 2peak, and when we consider when we consider all our cluster with at least 10 galaxies, we have 100% correspondences with 2peaks. That means none of those appear to be an effect, a spurious effect. No, it's a minimum thing that there should be correspondence, and this correspondence exists. Okay. Okay, so then what we did is an exercise that normally is not done, which is the detailed comparison between detections of two cluster finders. So this is our cluster finding in the right, and this is the cluster finder we are comparing to just for completeness, which is 2peak. And you see that there is a cluster detected. This is the convex hull of the cluster, and the radius there is the R200. So you see that the two peak correspondence is what we have there. So the two peak in this region of the sky and with the depth of the redshift detected for our cluster, the solution can be very different. In particular, we believe this is related to the friends of friend algorithm. The friends of friend algorithm to go into the connecting filaments. So this is completely different solution. In this case, whether there is no clear filaments, then the solution looks very much alike. And in this case, where the distribution is much loose, then the solution of our algorithm is completely different from this previous cluster finder. So in this case, there is a multitude of small groups, whereas we find a solution, we find a virial radius associated with that. So this is just to have a few examples that show the difference between the solution of the algorithm. It's not that one algorithm is good, one algorithm is bad. The algorithms are different for different purposes, okay? Okay, so the cluster catalog for us is the subset of all the clusters with more than 10 galaxies. This is our set, and it goes from, this is 0.14. We chose a limit of 0.14 and from 0.0009, and the number of clusters detected was 341, and when we compare these clusters with the existing clusters, we find that 75% of the clusters in the catalog with more equal to 10 or more galaxies, 75% of the clusters have counterparts as groups or as clusters in the literature, okay? So basically there is a remaining 87 cluster, which is about 25%, which we call the new clusters. New cluster means that they are new in the sense that they are not in the literature. It does not mean they are new in any physical way. So the reason for that, it would be incompleteness of previous catalogs or potentially difference in the properties. And in particular, the properties we will examine is the galaxy contents. Okay, cross-correlation, we cross-correlate with the REFLEX. We find 82% of, this is all completely automatic with the determination of the velocity dispersions. We recuperate 82% of REFLEX clusters. And the 5 remaining ones, we looked individually and found that we had problems of completeness of the data, or we have a close by galaxy or a close by star. So essentially, if we're not for those problems, we could have detected all REFLEX clusters in the region. Okay, so I will skip this. This is the connection with the DPO2, with the Propris. We have 50% agreement. 160C of our cluster were studied by the Propris with an Abell radius rather than the R200. And we will see that this is important because R200 in general is smaller than the Abell radii. So in order to get an agreement between our multiplicity, this is the comparison between the 166 clusters that belong to our catalog and belong to the Propris catalog. So what we had to do to get a good agreement in multiplicity, we had to extend our clusters from R200 to the Abell radius. And by doing that, we actually got a reasonable agreement between the multiplicity. Notice that the Propris got this in a semi-automatic way, and it was originated from the catalog of Abell. And this thing here was a completely automatic fashion. But when we compare the velocity dispersion we detect with the velocity dispersion given by the Propris, we find that the Propris, many of the Propris velocity dispersions that are considered to be valid velocity dispersions for cluster, they are overestimated. And this is expected because he was using an Abell radii, and so many galaxies that were not in the core were included, so they got a higher value. So we believe that our values are more physically meaningful. But this is again to get confidence. So we wanted to do all this to get confidence so as to analyze at the end whether the new detection had any physical meaning. Well, here is a comparison between the known cluster, that means in net, those that not in net. This is the comparison of the velocity dispersion. This is the comparison of number. You see that the new detection have lower multiplicity, so a big thing. The new detections have multiplicities that tend to be smaller. In terms of velocity dispersion, the new detections cover essentially the same range of velocity dispersion. And to a first reading, given that we said that there was a good correlation between the velocity dispersion and actual mass, we believe that the new clusters that we are finding have the same range of, thank you very much, the same range of masses. So this is one important fact that we are trying to argue, that the new detections are in the same range of masses than the previous, the conventional kind of clusters, okay? Okay, so I said already there was a way to separate early type galaxies from late type galaxies, and we define what we call a late type fraction. So for the galaxies in the core, we define what was the fraction of late type galaxies divided by the total number of galaxies. And we said that this was a raw, we call it the raw late type fraction, because due to the magnitude limit nature of the survey, we were not considering a minimum luminosity. So in order to make a comparison, a fair comparison, we need to introduce a minimum luminosity, and when we restrict the galaxies to make the evaluation of the fraction, when we include only galaxies brighter than minus 18.5, we call that the proper. So the proper, which is, the other one has a zero, this one does not a zero, and that is the one we care about. We want to be compared with apples and oranges with oranges, okay? So this is the way it works, the classification with which we heard the automatic classification of morphological classification. You will be able to reproduce this kind of study in the future with great precision, but this is to show that the separation between early type and late type galaxies, it works well. So I cannot go into the numbers, but the numbers here is the eta value, and the eta value separates the early type from the late type. So this is to say that we check a number of clusters. This is one of the new ones, and we found that the classification was working correctly. Okay, so this is a graph of all galaxies members of the cluster catalog. The color code is the early type, is the red dots, and the blue is the late type. So what we did is that we make a census, we make a count of the cluster within 0.04 to 0.09 for reasons. I can say that there is no strong redshift dependence of the efficiency of the cluster finder. Okay, so the cluster finder, it has a flat working between those two redshifts, and for computing the fraction of late type galaxies with respect to the total, we make a cut here at minus 18.5. So the calculation here is the calculation of what we call the proper fraction. Okay. So we have a volume limited and approximately complete sample. By reducing this sample to this redshift range, we are left with 207 clusters, and again, 154 of them are represented in net. And this is the distribution of the fraction of late type galaxies. So in the conventional cluster, we know that the mean value of the mean value of late type galaxy in the conventional clusters, I don't know whether you can guess the number, but the mean number that people give is 0.25. 25% are late type galaxy in the conventional cluster. So we find that the distribution of late type galaxies can go. There is a region here which is a maximum that would correspond to the conventional cluster, but there is a well-populated region with late type fractions that are higher than 0.5. For us, a late type fraction less than 0.5 is early type dominated, and higher than 0.5 is late type dominated. So this was approximated with two Gaussians, and we found that the two Gaussian, there is a 3 sigma significance for being a bimodal distribution, and these are the masses of the late type poor clusters. The masses extend mostly over the same range. This is the luminosity of the brightest, perfectly, the luminosity of the brightest galaxy, and we see that the luminosity of the brightest galaxies for the late type poor, that means the conventional cluster. For the conventional clusters, well, there is a tendency for having brighter cluster, central cluster galaxies. So this tells us that the new kind of clusters, that they have high late type fractions, they also have less luminous galaxies. Okay? And then, in order to see how does it look, one of these new clusters, this is one of the new clusters in a reproduction from the SDSS DR9. And you see that these are the late type and the early type galaxies. And you see that it's totally, you cannot recognize clearly the concentration and the luminosities of the galaxies do not tell you that there is a cluster there. This is the distribution of the early type and late type dominated clusters, and we made a first order correlation of this distribution. We find that the late type rich clusters do correlate. They have a higher correlation than the late-type poor clusters. So this has an importance in the sense that the relation between the late-type rich and late-type poor cluster, the relation with the large-scale structure appears to be different. And this would be in line with the theoretical prediction. So just to conclude and to get into the right time is the following. For the statistic, we call the statistical sample the one that goes from 0.04 to 0.09, and we find that 63% are dominated by early type galaxies. And they have a mean multiplicity of 22, and they have a mean mass by this number in units of solar mass by h to the -1, and we have 37% of late type dominated by late type galaxies with a lower, there is a lower multiplicity, mean multiplicity. However, the mass is not too far lower than the mean value for the conventional cluster. The statistical analysis shows that there is a 3 sigma confidence that the presence of 2 population components, and the late type rich cluster on average have higher ML systems, and they appear to be more clustered on larger scale than the late type poor clusters. Okay, thank you very much for your patience.
Well, thanks, Luis. We have time for a couple of questions.
I saw your cluster number around 300 clusters, and I used 2DF. Did you have any opportunity to compare with the Planck-Sunier-Zeldovich cluster catalog?
That's a very good point. This is work to do. It's the work to do. Just to mention that we have Sunier-Zeldovich clusters, which is a very good comparison. We have clusters also detected by weak shear, so this is the other thing. So the conclusion, which is not there, is that the masses should be confirmed by weak shear determinations. And the other thing is that this has relation with the LSST. If we believe that there will be clusters that are not the conventional kind of clusters, eventually that they don't have the same mass profile, then we will have to depend heavily, is my view, on the weak shear maps. So the weak shear maps are, for me, are the big tools with complementary with Sunier-Zeldovich, but the weak shear, I believe, it reveals the purest presence of dark matter concentrations.
Okay, Luis, that's a nice piece of work. So, but it seems to me that there are more informations than you can take from your analysis. For example, you are talking about dark matter clusters, okay? So, what's the scaling of that comes from your measurement? You know, because I think it's possible to calculate the height between the baryonic and dark matter, right? What's the scaling
that's a good point. Yeah,
because you are saying you are observing dark matter clusters.
Yeah. Okay. So, I would say that the extreme, if you go to ML, if ML goes up, eventually you can say, can we have dark clusters, just dark matter with almost no light, right? So, is this telling you, in a theoretical sense, is this telling you something about the ratio between dark matter and baryons, right? So, I talked to my theoretical on theory from good places that I can quote. And so they say, okay, you can expect in small systems, say galaxy scale, you can expect variance to be lost. They can be lost because they cannot be retained. But at the scale of clusters of galaxies, there should be, the variance should be, if we believe in a universal quotient for dark matter to variance, the variance should be there. And if the variance are there, in principle, you would think that the variance would be hot. And if the variants are hot, then you would believe that these things will show up in X-ray. So in the conventional view, the ratio is believed to be the same as everywhere. And why some of these variants did not get in the same proportion to form galaxies of the given type. Again, I have been talked to my friends in Chile now from simulations, and they tell me that the accretion of matter coming from some filaments, if they are symmetric or if they are not symmetric, I cannot believe them. They tell me that this accretion, which is has a direction, a special direction, has consequences in the type of galaxies you form. So you might have morphology of one type, of another type, because of the way that the dark matter baryon mix is being accreted.
Yeah, that's good. I agree with you. Yeah.
Okay, if there are no further questions, let's thank Luis again. And now we're gonna have a different game in town. Thanks, Luis. Great. We can talk more during the wrap-up. There you go.
Hello. Okay. Thanks for the organization for inviting me for the talk. It's, as Ricardo said, it's a different game. But what we have for the moment is an instrument that's being built that in the very near future may have a very strong synergy with LSST, can deliver in not so near future. And this synergy means the correlation between 21 centimeter intensity mapping measurements at redshifts close to us, which are between 0.1 and 0.5. And the galaxy distribution that LSST can detect in the future. We are working on constructing the instrument and preparing a forecast for 2020, which is when we expect to have the first light. And then after that, we can have real data from radio to forecast from LSST. So with that said, let me call you to the bingo game. Okay, the first motivation is that after CMB data from Planck and after the
latest results from galaxy surveys, including the DAS surveys that were released this year, and the Planck papers from, that were released in July. We get closer and closer to the precision cosmology goal, which is to set cosmological parameters to a very few percent numbers, which we are getting there. But still, we haven't answered inflation questions, and we haven't answered dark energy questions. So you have to search for information, to have more astrophysical and cosmological data to try to understand what these things are. I've seen here people talking about galaxy and cluster cosmology. I come from a CMB cosmology training, and recently I'm migrating to the 21 centimeter cosmology. And we can say that we are reasonably sure we walk in a reasonable safe path from 10 to the minus 6 seconds to about 380,000 years. That's when CMB was created, after matter decoupling from radiation. And then we don't know very well what happens from that time to the cosmic dawn and era of ionization, which roughly happened 120, 150 million years after the Big Bang. And a good thing to do is to use the 21 centimeter hydrogen hyperfine transition line to map this matter distribution in a complementary way of just measuring individual galaxies as we do in surveys. I'll go to that point in a minute. We can do with 21 centimeter cosmology, not at this point, but in a very near future, we'll be able to reach high redshift with these measurements when SKA, the square kilometer array, is active. We can reach redshifts to 6, maybe 7, maybe 10, and very optimistically, we can get to redshifts of 50. So, and this redshift interval here tells us what we can probe. Dark energy in this interval, curvature in this interval, non-Gaussianity in this interval. And for references, that's where we are, the time we are probing when we measure redshifts. And I will not talk specifically about the hydro-H1 bias here, but that's something that we have to understand and correlate with the optical bias for the galaxy distribution. So the 20 centimeter distribution follows a path that in frequency behaves like this, and that's the neutral area, that's the beginning of reionization, that's the destruction of the neutral hydrogen contents of the universe. And from about that point on, the universe pretty much fully reionized with very small portions of neutral hydrogen in galaxy protected areas, very deep, very with a large optical depth, so photons don't get there and ionize the hydrogen that's in there. And there are effects here which are caused by absorption of CMB photons, and then the decrease of this line when the heating of the universe starts, and then we reionize the universe, and then the reionization, the destruction of neutral hydrogen goes up to redshift is equal to 6, maybe 7. And using the 21 centimeter line, we can get to this area here and go down and check complementary way the matter distribution using the hydrogen as a tracer. So we have redshift history and other stuff that's interesting. And the 20 centimeter can help us to go maybe here with the square kilometer array. And this part here is equivalent to this part. And many recent instruments will check this part here with Z less than 1 for to probe the time where dark energy starts dominating the universe. So we use something that's called intensity mapping, which is complementary in a way to what optical surveys do. Instead of mapping individual galaxies, we get the radiation field that's emitted by galaxies and by intergalactic medium. And then you pretty much, it's like if you have a poor view, or if you need glasses, if you had glasses, you would see something like this. With no glasses, and the general feature would be something on the right. These are simulations. The red galaxies here are the strongest ones, which you can get after an hour of integration with VLA in New Mexico, and both are simulations. So this is 0.5 degrees, and we are talking something that's much smaller here, like 1 arc-minute or 2 arc-minutes here. And this is a quick survey of instruments that will do intensity mapping, not only hydrogen, but carbon and oxygen, which are the most abundant elements you can see in the universe. And the instrument I will describe to you in a minute will fit somewhere here. This is redshift, and this is the relation between the largest declination area you cover in the sky and the resolution of your instrument down here. So the lowest boundary is resolution, and the highest boundary is the declination you cover in the sky. So
sorry, what determines the sensitivity to redshift?
That's what determines the sensitivity for redshift.
Yeah, but why are some sensitive to small redshifts and the others are sensitive to?
Well, the instrument that you design has a frequency dependency, like the electronic frequency electromagnetic wave that sets redshift. So you have 1420 for the rest line of the hydrogen. Then you go down in the frequency, you go higher in redshift. So bingo, you do 6 megahertz, 12.6 is redshift 0.13 to 0.48.
So it has to do with the size of the antenna, the detector?
And the detector, yes. Mostly the detector, the band pass that you decide to do, because it has a lot to do with how you clean your environment with the frequency from mobile phones, for airplane transmitters, radio stationary satellites, and so on. So you try to get a band that's as clean as you can get.
That's how you decided to have this band?
For bingo, yes, yes. Nobody's doing this, as you can see here, except for a sphere that will happen sometime in the future. That's a satellite. And nobody's doing here. Everybody's getting before dark energy starts dominating the universe. So that's complementary to most of the other surveys. And I'll tell you in a minute why we decided to do it. So the main science goal we are trying to understand dark energy features. The main science for bingo is baryon-acoustic oscillations. We have other science targets, but BAO measurements in radio is the first target. You move from here to here in observations, and you move from here to here in data analysis, right? And we are trying to get something that happens about here at 150 megaparsec scale. That's the acoustic scale that you measure in the CMB data. That's the time, that's the acoustic scale. We can use as a standard ruler, and BAO, what you see in the CMB, you expect to see back in a nonlinear time of the universe in the galaxy distribution. If you could see individual galaxies in this clustering, you might expect to have an excess of galaxies in the correlation function around 150 megaparsecs from any given galaxy. And the way you do that for intensity mapping is having this flip of the hyperfine hydrogen transition. And people should ask, why are you going to do that in radio if we have already detected in optical with a very nice signal to noise, with a very systematics and most of the physics detected? I would argue that it's complementary because we have different systems we can probe different redshifts, maybe even deeper redshifts. We can use the universe, the hydrogen to map a large fraction of the universe. We can have hyperspace slices, so we have a data cube of radio measurements. So you can have BAO in the transverse direction and in the line of sight direction and transversal direction. So you can have luminosity distance and angular distance in the same measurements. It's an efficient alternative for measuring individual galaxies, and you can bring what we learned in 45 years of CMB measurements to 21 centimeter data. Most of the tools that we use for statistics, for 2D distribution of a diffuse radiation field can apply almost straight from CMB to 21 centimeter mapping. That's in the specifics of our choice. Interferometers are great. Most of the instruments that do 21 centimeters are interferometers. They are great, but expensive and hard to maintain. And complementary approach, which has its pros and cons, are single dishes with many horns per dish. It would be equivalent in optical to have many CCDs for one single telescope. And what we want a large collecting area. We want a large area on the sky. We want, that's a specific for with low side lobes and a good, very sharp beam. You would want a lot, long observation time. You would like to have sensitivity in the scales where BAO will appear band, which is, I'll give you the frequency in a minute. And the redshift range is around, this area is good because after that bias is larger than 0.7 and you have a lot more work to account for that. And for your reference, 1300 megahertz, that's this redshift. 100 megahertz is this redshift. But as we have more and more RFI, which for radio frequency interference everywhere you can think of. So that's not, it's understandable that people go to the deserts of South Africa and Antarctica and Australia for radio telescopes, to Atacama in Chile. You want places where people don't turn on mobiles and talk while you're doing measurements, that people don't turn microwave ovens while you're doing measurements, that people don't have horizontal links talking to people, farm to farm while you're doing your measurements. And that's almost impossible, as you can imagine. But there are some places that we can still count on. So that enters the telescope. I'll give you quickly the concept. It's a single optic with two dishes, which make a focal plane instead of being large, make it more compact. That's a resolution for your arc minutes. The horn opening is quite large, 25 degrees. That's the frequency range. Channel resolution, it will be better than 1 megahertz at this point. But for computation, you have 300 megahertz here. You can count up 1 megahertz per channel. And that's redshift interval. This is some of the instrument characteristics. This is not true anymore. We may have a system temperature a little bit higher than that. But I would like to stick to these things. It's a fixed parabola. There's no moving parts. It will be a transit telescope. All of the electronics are off the shelf. And simplicity is the idea, to make it as easy to build and as easy to maintain as we can. The current status now is that it's under construction. The horns transitions, they've arrived from fabrication this week. So this is done. Receivers are half completed. Measurements are completed. We did that all over last year. There was a paper on arXiv last month summarizing the measurements and the site selection that we had. The topography is sorted out, legal issues are sorted out. And that was the status 2 weeks ago, and I forgot to update. We are now 100% funded. We got the equivalent of $4.5 million for the full construction. Give you a quick overview of the optics. We have the horns here. That's looking at declination minus 15. You get the primary, secondary illuminates the focal plane here. This is 45 meters. This is 34 meters. For your idea, none of the dishes will fit in this room. They are larger than this room. Both. The larger one pretty much sits in half of a football field. That's the number you can have in mind. This is what we are considering for the structure. This is being calculated by an engineering company, and it will sit I'll tell you about the site in a minute. So this last week we've been doing simulations on the optics. This is the horns that we have for the plane. This is the response for the central pixel. There's two here. That's polarization and intensity that you have. This will be the array. One of the configurations, the central pixel, you would see things like this. From the border, this minus 60 and 6 would be this view, and this view here. And then some other measurements of the beam for individual horns. Some other measurements, and then that's a receiver that's being built at INPE. That chain is already tested, and it works very well. We are waiting for these components to arrive from China by January 15, so we can fix the main receiver by, let's say, mid-February should be completed. The horn are built. You guys know what a corrugated horn is, right? It's a horn, it's like a vuvuzela that you use for football noise, with rings inside for better propagation, for mitigation of cross reflection, and to reduce side lobes. Think of a horn that goes from here, where I am, to where Rogério is sitting, about half a ton. And that's pretty much what this looks like. It looks like maybe a rocket tip or maybe like a submarine. So you can have an idea of someone who's mounting it. That was developed at a company close to where we work in São José dos Campos. And that's someone who can sit inside it. It holds myself 120 kilos sitting inside of it. No deformation. No tilting, so it might fit probably Ricardo, myself, Rogério, Mariana, Sandro. The five of us would just get in line there. So these are polarimeter transitions that will separate the radiation in two polarizations here. Then this part you go to the receiver. So it's taller than I am. It's like Ricardo's height probably. That was delivered last week, and we tested these parts also last week. They are working almost okay. We have some fix to do in the polarimeter. Another picture of, so all the way it's going to be about 6.2, 6.3 meters from the opening to the receiver, roughly. So some tests that we did at Lychee, I'm not going into details here, but I can tell you that the testing was pretty much like a textbook result. All of us were impressed. The guy who designed it in France was impressed. Us who built it were impressed. We didn't believe it would work so well. And Bingo will cover this blue area here. There has an overlap with this. I tried to send a message to Ricardo when he was in Campinas 2 weeks ago to get some information on this. We can talk in January after you remove your Christmas hat. And I will go quickly on what we are working on. Forecast for the foreground and for component separation. This was done Bigotzazi 2015, but it has to be recalculated for the new bingo configuration. Also, component separation, mostly dominated by synchrotron and by point sources, radio point sources. We have to recalculate that for the new optical configuration. But we are setting up to 7 to 8 PCA modes for separation. And then we have to work on a power spectrum calculation that was done by Lucas Olivari in 2017. We need to recalculate. I see Karin here. That's the sketch of the pipeline that is being developed in Manchester. There's one separate pipeline. There's another one that's been developed at USP. So we have two currently, they are not competing, but they are independent. So this one is mostly developed by Clive Dixon and Stuart Harper. The one is based upon open code that was developed by some of our collaborators in Zurich. Then it's adapted by Filipe Abdala, Lucas Olivari, Karin Fanazier, some students. For site selection, I mentioned about radio frequency interference. That's what you usually see in a place that's in the middle of Rio Grande do Sul, the southern part of Brazil. You have mobiles, you have aircraft transponders, you have airport radars, you have TVs or other mobile. That's what you do not want. And that's what you would like to have, and that's what we found in Paraíba, the northern state of Brazil. So it's a clean environment, no mobile phone, nothing. After 4 campaigns, totaling about 8 hours of measurements. Yes? Yeah, that's single band. That's where we measure.
Okay.
That's a measurement, and that bingo, 960 to 1260. So we opened up the band here. That's 960 goes from here, 1260 here. So you can. I didn't decide to put the green area because it's pretty much all the plots. So. But the green, everything you see in the paper of our RFI measurements, the green area is always our band. But we still have to worry about airplane coverage. We have the primary site here, a secondary site here for some other science that we do in the work in the future. And that's airplanes that the ones who go this way, you go to US, the ones who go this way, you go to Europe, and some go crossing from the capitals in the coastline towards the west part of Brazil. This is accounted for. We haven't measured any during this campaign, but we didn't have sensitivity for geostationary satellites. We expect to have them bothering us most of the time. We have to mitigate this. This is the bingo bands here. The main problem is that you have a central frequency for geostationary satellites, but you don't have filters that avoid the emission, which is really powerful. Into harmonics to the sides. So we expect to have this contamination, and we have to find a way to mitigate in hardware. So I'm reaching the end of it. That's where bingo will sit, in Paraíba. That's the geometrical configuration of the telescope on site. It's a land of 300 by 200 meters, a small area. Sitting here. And you have wind bills here, and we visited these sites. We visited 11 sites total in Paraíba and 6 more from Rio Grande do Sul to the north. That's a picture of the place. That's winter time. That's after a few days of rain, and that's after 3 weeks of rain. I mean, sorry, that's after 2 years of no rain. 2 years of no rain. And we are working on a silent zone proposal in conjunction with Anatel, the International Telecommunications Union, and the state of Paraíba to try to have silent zones here. We have layers. The main layer is telescope only, no mobiles, no microwave oven, no zone 2 says no industrial activities, no power plants, no radios, no Wi-Fi network, no radio repeaters. You're going to be isolated, you know. Zone 3, no new mobile tower, and zone 4, we keep what's in there. Anything new that has to be installed has to request a permission. So we try to make it as clean as possible, but it's like entropy. You try to remain constant, but it grows. It may grow slowly, but you ever grow. So we try to mitigate it for as long as we can. So additional science that we can do besides BAO is matter density, redshift distortions, anisotropic balls, life history of hydrogen, radio recombination lines, mostly sensitive to hydrogen, galactic continuum. That will be a science separate case for synchrotron determination of the galactic properties for the synchrotron emission, and fast radio bursts, which will come for free, because you'll be observing the sky, same area, same time of the day again, and we have to prepare to understand the energetic of this phenomenon, which is a known phenomenon. The main difficulties we have at this point is a large telescope that we need to find a company to fabricate the dishes. We don't have it. We need to reduce the cost of the horns. We need to understand better our receiver to mitigate this thing here, the 1/f noise, which comes from the electronics. Calibration stability, we don't have pointing capabilities, so we have to look at what crosses the beam in a given time of the month. Our side lobe pickup seems to be okay, but the design is very good. The horn worked fine. We have to test for the full optical system. We have to keep the mobile quiet zone and the RFI quiet zone as long as we can. Atmospheric fluctuations is not an issue for us in our frequencies. You have a very bright foreground, which is about 4 times brighter than the measurement. We are doing techniques. That's what the pipelines, one of the crucial items in the pipelines, component separations. We have to deal with diffuse galactic radio emission, natural galactic point sources. And before Ricardo raises the hand to me, these are the bingo players. So it's been led by INPE, USP, and the Universidad Federal de Campina Grande. The original concept was developed by Manchester. They have some participation at this point, but it's not as strong as it was in the past. We expect to have them closely working with us when the telescope is running. We have a strong participation of one person UCL, that's Philippe Abidala, on pipeline and data analysis efforts. Optical design comes from France. Money for components and some theory comes from Yangzhou University. Part of the electronics came from ETH Zurich. KwaZulu-Natal has someone from the theoretical cosmology side that's interested in component separation. And we are trying to keep Uruguayan colleagues on. They've been dismissing after the site that was originally designed to be in Uruguay. After we moved to Brazil, most of our Uruguayan colleagues lost most of the interest. And so that I will finish with this. Thank you. Merry Christmas.
Thanks, Alex. I'm a bit concerned because I think your horns are actually Daleks from Doctor Who. Exterminate. So do you have questions? Two-way.
Is this working? Oh, okay. So, so is the plan for calibration mainly with natural sources, or you guys have internal?
Well, we have to have internal calibration. At this point, we are using CoFETs as in the Magic T. So we have two outputs for the receiver with the polarization separation and one input for the CoFET. But it's not stable as we wanted. So we are still trying to get a better solution. We are not thinking about using cryogenics because it raises the price for like.
Okay, so nothing is temperature controlled.
Yes. Well, it will be temperature controlled, but it will not be cryogenics.
Okay.
We try to keep as stable as we can with either heater or cooler inside the boxes.
So mainly electronics, not the horn.
Yes.
So, okay, thanks.
And on the outside, whatever crosses the beam.
A very interesting project. My question is from my ignorance of 21 centimeter studies at high redshift, how this project of yours, the Bingo, complements to the other surveys of 21 centimeter high redshift observations. Maybe I got lost in your introduction, but the complementarity with the current.
Yes, most of the other, I guess all of the other instruments that are running, they are at so they start at 0.5, 0.6, 0.7, and we stop at 0.8. So we have we are not an interferometer. Most of them are. We have some single dishes that do it, like Green Bank Telescope and the Park Survey in Australia. But the concept and what we have, you know, Green Bank is not like that, Parks is not like that. But scientifically, the main complementary comes from redshifts that we do not border, but we closely border where the others start. So there will be measurements in a frequency that will be closer to us after dark energy starts dominating the dynamics. And these guys are doing, you know, more horns, more telescopes, but at a frequency range where dark energy starts, is not dominating yet. When matter is losing its dynamical power, passing through dark energy. So that's the main goal. We'll be alone for some time, at least.
More questions? Oh.
So Alex, for you, is the radio noise more or less important when you have a single dish when comparing to having many dishes and doing, you know, like SKA is doing? Is it similar kind of problems, or do you have, I mean, what kind of sensitivity are you aiming for in the end here?
I can tell you the system temperature, that's 50 Kelvin. I think the main complication for us is that for this noise that comes from that are not astrophysical sources, but the local sources, interferometers can better than we do. So they can clean up this RFI measurements through interference. The time delay in the dishes help dealing with the noise better. The angular resolution of interferometers are much smaller because it's a baseline that will deal with 1 arc minute, maybe less than that. We have a broader, but our collecting area, okay, forget SKA, which is another game. We not talk about SKA, but we do the complementary thing in terms of easiness to do the data analysis, because doing the correlation in radio is very complicated. We have to worry more about how we clean the noise, that's environmental noise. But on the other hand, our receivers are easy to calibrate and to do a pseudo But you'll be complementary in this aspect as well.
And another question: comparing to other single dish 21 centimeter experiments, how does Bingo compare? For instance, they have, of course, the huge one in China, the FAST, right? And is there anything Bingo does that FAST wouldn't do? Because I didn't remember in your.
I didn't mention FAST, but
just maybe different area of the sky, I guess.
different parts of the sky, different frequencies, and the receiver. I don't remember from memory now, but the receiver in FAST has a worse system temperature, much larger collecting area, but we have 50 horns, like 50 CCDs, looking at close areas of the sky. So that's again that mimics. Even if you have a system that's better, we have 50. It's like 50 separate instruments looking at very close areas of the sky. That's the gain, and that's one of a kind.
More questions? Oh, well, if not, let's thank Alex again. And head to lunch on an Italian restaurant, is that right?
Com gorrinho, sem gorrinho, né?
Oh.
Beleza.